All right, we're going to cover a few things in this lesson. This is basically 2 or 3 lessons in one. First up is exponential growth and decay. And you might have heard this phrase back during COVID, or maybe you didn't pay attention back then because you were, little. But, exponential growth basically means that something starts off small and then gets really big really fast, kind of the way COVID spread. At first there was a few cases, then there's a few more, and then a few more, and then a lot 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 more, and it kept going. So like linear growth is a straight line where it goes like this, it kind of goes up and up and up at the same pace. Exponential growth looks more like this. Starts off and then it starts zooming up like that. And decay is just the reverse direction. Decay is like if you have a bowl of hot soup, for example. It starts off hot. The longer it sits there, the faster it's going to cool. So all of a sudden, it's not hot at all. It's just room temperature. And that would look more like this. So that's what growth and decay is. One is getting bigger faster, and one of them is getting smaller faster. There is a formula to use for it. And it's almost the same formula, except for one sign difference. So for growth, your formula is y equals a parentheses 1 plus r raised to the t. And then for decay, y equals a 1 minus r raised to the t. So what does all this stuff mean? It's pretty straightforward. The a, this is your initial amount, your starting amount. So a is your starting amount. Just like we had before, we had y equals a times b to the x. It's the same idea, just b actually has a little different values in here now. R, this is your rate in decimal form. So if it says 8% growth, it means 0.08. If it says 12% decay, it means 0.12, not 12. And of course, t is your time. Could be days, months, years, depends on the problem they give you. So you have to pay attention because if it says the time is 1 year and it says, oh, here's 6 months, well, you don't put 6, you would put 1/2 because 6 out of 12 is 1/2. So you got to pay attention to what the problem says for the time. So we're going to give you a table here. It looks something like this. We'll have 0, 1, 2, 3, 270, 90, 30, 10. They're going to ask you, is this exponential growth, exponential decay, or neither? So the thing you have to remember here is that with these functions, on your x's, it's always going to be changing by 1, or should be changing by 1. Plus 1, plus 1, plus 1. So now, on the bottom, what you want to do, you're looking at this, and you can just tell it's going down, right? 270, 90, 30, 10. It's going down. So what we do is we take these first two values here, and I'm going to go 90 over 270. And I'm going to reduce that to 1/3. I don't want to do 270 over 90 because that's saying 270 divided by 3 is 90. We're not dividing here, we're technically multiplying. So each one of these is being multiplied by 1/3. So that would be decay. If your rate is, more than 1, that's growth. If it's less than 1, but more than 0, that's decay. So decay is less than 1. Growth is more than 1. So this one would be decay. Let's do a second table here. 0, 1, 2, 3, 5, 10, 20, 40. So again, make sure this is the same change up here. So this is plus 1, this is plus 1, this is plus 1. So far, so good. Here is getting bigger, so try multiplying it. So 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. So it is the same multiplication every single time, which means this is an exponential growth function. Try this one. All right, pause it, do the answer, come back. All right, so this one, you're going up 1, up 1, up 1. Down here, you're going times by 1/2, times by 1/2, times by 1/2. So this is a decay function. Okay, so we have a music festival here, and its first ever year, it has 150,000 people at it. Your attendance increases by 8% each year. So they want you to write a function that represents the attendance after T years, and then figure out how many people will be attending the festival in the 5th year if the numbers hold. So we're increasing, that's a growth function. So y equals a 1 plus r to the t. So a is your starting amount, so a is 150,000. R is your rate, that says 8%, but change that to a decimal, so 0.08. And now you're going to plug it in. So y equals 150,000, parentheses, 1 plus 0.08 raised to the t. And then make it a little prettier. Y equals 150,000, parentheses, 1.08 raised to the t. So that's the first part. There's your function. That's what it looks like. Now, we have to figure out how many we should be attending in the 5th year. And this is a little trickier because your brain wants to plug in 5 for t because 5 is the 5th year, right? In this case, it's not. Your very first year is t equals 0 because that's your starting point. So then you have your next year, t is 1, next year, t is 2, t is 3, t is 4. So year 5 is actually the value of 4 for t. I know it's a weird concept, but t equals 0 is your first year. So now we just got to plug the value in. So 150,000 times 1.08 raised to the 4th. And once you push your buttons and get your rough answer, it's around 204,073 people. All right, similar problem here. Website has 500,000 members in 2020. The number Y of members increases by 15% each year. So again, growth. So write the function, okay. A is 500,000. R is 15%, which means 0.15. So let me write my equation. Y equals 500,000, parentheses, 1.15 to the t. I skipped the whole 1 plus 0.15 step because that just seems useless to me. So now they want to know how many members will be there in 2026. So now you got to figure out how many years that is. And in this case, the whole t equals 0 thing is not really necessary. So from 2026 to 2020 is 6 years difference. So 500,000, 1.15 to the 6. And that gives you just over 1.1 million give or take. We're going to do part A and B. You're not going to graph it right now. You can graph it on decimals if you want to and check it out. So your car is losing value. So this is decay. So y equals a1 minus r to the t. So your A is 21,500. Your R is 12%, or 0.12. And T is the time in years. All right, so now plug things in. Y equals 21,500 times 1 minus 0.12 to the T. So 21,500, parentheses, 0.88 to the T. And of course, equals Y. So there's your function. Now, to find its value after 10 years, you would plug in 10 for T. So 21,500, parentheses, 0.88 raised to the 10th power. And when all is said and done with that, you're going to get roughly $5987.77. So that's what decay looks like. Started out pretty decent and then went down pretty fast. And that's the basics of growth and decay. So next up, we're going to look at modeling with these things. Okay, so modeling with exponential functions basically is a fancy way of saying word problems. So for these, we're using the original one, y equals a times b to the x, where a is your initial amount and b is the rate of change. So it's not the growth and decay formula, it's the original one. So here, we've got a graph that shows us the population of bacteria after X days. It wants to find the population after 12 hours and after 5 days. So first, we've got to find A, our starting amount. Well, right here we have 0 days, which is our starting amount. So that's 3 bacteria. So A is 3. Next, to find our B, we're going to make an XY table. So 0, 1, 2, 3. So 3, 12, 48, 192. So again, I'm going to take these two numbers and divide them. So 12 divided by 3, that's 4. So each time it should be 4. So this is times by 4. This is times by 4. This is times by 4. So my B is 4. So I have y equals a b to the x. B is 4 and a is 3. So there's your function. And now they want it after 12 hours, after 5 days. Remember, x is each day. So as I mentioned at the start of the lesson, we got 12 hours. That's not days. So to find that one, I go 3 parentheses 4 to the 12 over 24, because that's 1/2. It's a half a day. So it gives you 3 parentheses 4 to the 1/2, which is going to give you 6. Because 4 to the 1/2 is the square root of 4, which is 2, times 3 is 6. So after 12 hours, there's 6 bacteria. Now they want 5 days. So same idea. 3 parentheses 4 to the 5th. That's going to give you 3,072. Right, so this one says our table shows us the amount Y in milligrams of caffeine in someone's bloodstream X hours after drinking coffee. So we're going to write the function and then predict the amount of caffeine in the bloodstream after 6 hours. So again, we're going to have Y equals a b to the x. A, well, we have our time is 0, so that's the starting point. So 125 is A. So now B, little trickier, I will grant you. We're going to be dividing this by this, or this by this. It doesn't matter. It's all the same answer in the end. So I'm just going to go 80 over 100. That's 0.8. So my B is 0.8. So my function, y equals 125 parentheses 0.8 to the x. And now you got to plug in 6 hours, so x will be 6. So 125 times 0.8 to the 6, and that's going to give you roughly 32.768 milligrams. Pause the video, find your function and the number of trout after 6 years, and then come back to the answer. All right, so we have y equals a b to the x. A will be 48, because that's our starting point, our 0. To find b, I'm going to go ahead and divide. If I take 72 over 48, that's going to give me 1.5. And each one of these is times by 1.5, times by 1.5, so on and so forth. So my b is 1.5. So my function, y equals 48 parentheses 1.5 to the x. And I want it after 6 years. So replace the x with 6, 48, 1.5 to the 6. And that's going to give you roughly 547.